with that, I'm going to hand it over to Nafeez. Please make him welcome.
Hi. Thank you. So I guess people are still flowing in, Friday night parties. This is my first DEF CON. Talking in front of a lot of people, a little nervous. I hope I'll make it till the end properly. All right, so a little bit about myself. I'm Nafeez. I've been doing web AppSec research for a while, mostly interested in JavaScript static analysis, wrote a few tools. I've been recently learning to write some good code, so I've been doing some development up recently. And one of my main projects right now is Asset Watch, where it's a transparent attack surface discovery as a service. Check it out. And please follow me on Twitter at skeptic_fx. Okay. So for most of you here, you might be wondering what is the topic about today, compression oracle attacks on VPN networks. What I'm going to talk about today, the end goal, is to basically break VPN networks in a very generic fashion. And I'm going to specifically take one of the well-known VPN providers, if you know OpenVPN, and we'll see a demo of how to leak secrets from encrypted traffic. Okay, let's start with compression, because that's very core of what I'm going to talk about today. Because this is a much broader audience, I would like to explain more in detail about what is compression, what is an oracle, what is a compression oracle, and how these attacks work in general, and then go into how this applies to VPNs. All right? Okay, so compression. In computer science, one of the common things that people use is compression, ultimately which gives you reduced bandwidth, and it saves a lot of money for the client, for the client side and the server side. So it definitely makes sense to have good compression algorithms. So over the years, we've been having very good compression algorithms. One of the famous ones that we know is the LZ77 family, which has this LZO and LZ4 compression algorithms. So in this case, the way it works is by replacing redundant characters. As it's obvious from here, you can see the sentence which has everything looked dark and bleak, everything looked gloomy, and everything was under a blanket of mist. In this, you can see everything looked is a very redundant pattern. So a compression algorithm who's trying to compress this piece of data is not going to repeat them. What it's going to do is replace it with the codes within the existing stream. So when it compresses the data, it's going to say -34,18, which eventually for when on the decompression side means just go back 34 characters and expand the next 18 bytes. And so for whatever makes sense. As long as the final output is much more reduced, the compression makes sense. All right. Another well-known technique is Huffman coding. So what we have been seeing so far is compression at the byte level. Huffman coding, hey, you know what? You have a lot of these characters. I don't want to waste 8 bits for every character. What I'm going to do is just see a frequency mapping and take the most repeated characters and assign them short bits instead of one whole byte. So in this instance, this is a sample of a frequency table for Huffman coding. So characters like space, A, all these characters are going to have much shorter bits. So in this case, it's just 3 bits for A and space and E. So ultimately, you get when you do use this for compression along with the previous algorithms, you get a much more reduced number of bits. So in real world, you have this algorithm which combines both of these called dflight, which is the ones that are commonly used in gzip, the zlib library, and also if you have been hearing about TLS compression, which got disabled a while back when it was around for a decade. that use deflate. So with the understanding of data compression, let's go and think about compression side channel. So what does that mean in the context of today's talk? So around 2002, this gentleman called John Kelsey, he came up with this white paper called Compression and Information Leakage of Plain Text. So in the crypto community around that time, people were talking, it's very well known that when you take a piece of data and compress it and then encrypt it, a lot of bad things can happen. So what he said in that paper from a high level, I would like to explain from an infographic. So before we go to that, it is well known also by that time, and even it is always true that when you have encryption, whoever is trying to snoop into your data can always look at the length of the data. There is no mathematically well-known way to hide data, hide the data, the length of the data when you compress them. When you encrypt them. So even though encryption scrambles all your data, it doesn't prevent the attacker from understanding how many bytes of data you encrypted, right? So that's pretty obvious. So in Wireshark, or if any man in the middle is going to go and look at your encrypted data, he's going to get the data length. All right, so let's try and understand this from an infographic about what the paper says. So assume a black box which does compression and encryption, which takes in plain text data and gives you encrypted data. And obviously you'll have the length of the data as well. All right, now in this case, if you have an attacker who can add or append some piece of data that he controls to the existing plain text data, even though he doesn't have to know what the plain text data is, and also if he can observe the encrypted traffic, then what this paper tries to say is you have a compression side channel possible, and you can have a compression side channel attack. So what a compression oracle attack in theory means is that from an attacker's point of view, an oracle in crypto efficiently allows him to brute force secrets. So in this case, we have a compression oracle attack. So what that means is using compression, the attacker can have an oracle which efficiently reduces his amount of brute force that he has to do. So let's say the secret that he's interested in is 4 characters. So that would take, if I have to do a dumb brute force, that will take 10,000 requests. So I need to brute force each and every character for each and every number. Now, so that's provided just for the numbers, not for alphanumeric data. Now, with the compression oracle, you can do that efficiently with, or any, not just compression oracle or any kind of oracle, you can do that efficiently with just around 40 requests. So all the attacker have to do is send 40 requests, and he can efficiently get the final secret, which is 4 bytes length. Now, in any kind of oracle attack, like you might have heard of this attack called padding oracle attack, right? The attacker's final goal is to choose a specific byte, which also participates in the data compression with the existing secret. So let's see that in more detail in the upcoming slides. So I've tried to put an infographic of how this would work with actual secret data. Imagine you have a set of plain text data at the very top, which is what the application is trying to encrypt. So this could be a browser or any email client, things like that. Now, assume that the attacker can also inject some data to the end of that. So the final output would look like one on the top, right? One above the compression block. So once that comes out of the black box, what the attacker can observe is the encrypted data length. So as we already said, this is what the compression oracle here is. So he can look at the length, and he can also inject his own bytes. So if you see this interestingly in what he chose here, the whole data before compressed, that's the ones on the green, those can be compressed. So the stream secret equals and the secret equals that the attacker injected are compressible. Now, of course, the one here doesn't match with the sits, which is the actual secret that he wants. So he keeps brute forcing that. 1, 2, 3, 4, 5. And finally, when he sends a request which has sits in it, the compression length increases. Finally, what that efficiently results in is a smaller length of the data packet. So if you increase the compression length by choosing a specific character, you could reduce the encrypted length. So in this case, you've been having 30 for other secrets, other characters, but the moment he chooses the right one, it becomes 29. So that's compression oracle from a very high level, right? So all that is good. Nobody talked about it after that. People just talked, say, if you do compression and then do encryption, things can go bad. Okay, so what? Now, people have been talking for some time after that, for the last decade, about how can we make this into a real-world attack. So if you think about this, what an attacker really needs to make this into a real-world attack is to inject bytes and to observe length. So let's try to think about that. Observing encrypted traffic length, that's pretty straightforward. All you have to do is a man-in-the-middle attack, right? And the other requirement is the most interesting one here, which is adding the attacker's control bytes into an existing stream of, into an existing application which already does compression and encryption. So browsers are a very good target for this. So browsers have this thing called the ambient authority, wherein anytime a request goes out of to a specific domain, the browser sees if the cookie jar has this specific cookie for this domain and automatically attaches it. So if you are sending a request from a.com to b.com, the browser always sends the cookies for b.com regardless of where it originates from, unless you have specific things like same-site cookies and stuff, which are very modern. Now, also, the browser allows you to send simple cross-domain requests with the post method, which means the attacker can inject his own post message body and send a request to, say, facebook.com. And the browser chooses the cookies for facebook.com, and the attacker gets the secrets, what he wants in the existing payload, and also he can inject his own brute force characters into the whole stream. So this could effectively come up with a compression oracle attack in a real world using browsers. So in 2012, you might have heard of this attack, a very famous attack called Crime. So Crime was trying to do compression oracle attack on TLS compression. So up until 2013, all browsers or most of the TLS clients were doing TLS compression enabled by default. So which is part of the TLS spec, and all these browsers had them enabled as well. So even protocols like Speedy, which is the precursor to today's HTTP2, had them. So what these guys did, Julian Rizzo and Ty Dawn, where they were able to do a real-world attack of compression oracle on websites like PayPal and GitHub and stuff like that. And the most interesting thing about their work that I loved is that they also predicted the attacks that would come in the future, right? So they also said HTTP gzip may be also vulnerable to this, and they also provided examples, but their research didn't talk about how this would happen in a real-world attack for HTTP responses. So later, in 2013, the famous attack called Time also came about. So wherein they talked about two interesting new researches, which is, I would say one interesting new research, which is you don't have to be a man in the middle anymore. You could just do the whole attack by using timing differences within the browser. So they would send requests from the browser, and using TCP window channels, window sizes, they were able to use that as a oracle instead of being a man in the middle. And of course, they use the existing research on crime to leak HTTP responses. So even at this time, I would say things were still, when it comes to compression oracle attacks, things were still little theoretical, and there was no real world, people are not really afraid of using this attack. Attackers are not able to easily use this attack in the wild. So breach came about. So breach was very interesting, even though it didn't come up with any pure new research in terms of what the attack already was doing. These guys, Angelo, Neil, and Yoel, they added a lot of real world properties into this attack, which means what I'm trying to say is they were able to come up with tools which could make this compression oracle attack really possible on HTTP responses. Because by that time, HTTP requests for compression has been disabled. So the breach attack was pretty famous, and it got a lot of press attention as well. You might know about them. So around till 2015, we've been having other attacks as well, like the Heist, and then we also had some more research on practical developments to breach. So all these are history. I'm sorry if I've been a little boring and monotonous so far. I'll try to make it a little more interesting, because this is going to be my section now, which is what's going to be new today. Obviously, it's the VPN tunnels. So far, all the attacks on compression oracle attack have been purely talked about, and the real world attacks have been on browsers using TLS. Now, what if all these are fine, and what if you're using VPNs? And what could go wrong if you're using VPN to connect and browse a website? Let's try to think about more about how VPNs work. So when it comes to the topic of VPN, I would categorize it as a few classes of VPNs, like the corporate ones, the IPsec VPNs, and the more modern ones, which are the TLS style VPNs, right? So what I'm talking about are VPNs like these. TunnelBear, the Spear VPN, all these pure SaaS style VPNs, where as a normal user, you could go and connect, you create an account, and for $10 or $7 a month, you can have a VPN connection. So what do all these VPNs have in common? Well, they use OpenVPN. So OpenVPN, up until recently, was one of the most commonly and easily used VPN. There have been other VPN solutions as well, like Algo VPN and the upcoming WireGuard. If you have been at Black Hat, the upcoming WireGuard is pretty interesting. So regardless of those VPNs, we are going to talk about how OpenVPN in general can be attacked, which is eventually used in many other VPN solutions. So from a high level, this is how a VPN in general works, but very specifically, this is how OpenVPN works. They effectively use a lot of TLS protocol within themselves, and also use existing OpenSSL libraries components. So if you look at their code, they heavily use OpenSSL. So all the encryption and all these related stuff are already done. They are not rewriting all of these code. So the first thing that happens is a control channel where they negotiate the parameters, what protocols I'm going to use and what compression I'm going to use. And if compression is enabled, what they're going to do is compress the whole data channel before encrypting. And this happens by default on OpenVPN. So what do I mean by compress everything? So they compress the whole data channel, which means regardless of your underlying protocol, whether it's UDP or TCP, they're going to just compress it. So if it's HTTP, it's going to be TCP. And if it's DNS traffic, they're going to compress that as well, which is UDP. And it's bidirectional. So not just the HTTP requests would be compressed, even HTTP responses. So you are effectively having something similar to crime and breach together. And the compression algorithms they use are not deflate. They are just using the pure LZ77, which if you remember from the start of the talk, we discussed how LZ77 family of compression works. So they're just going to replace existing bytes. There is no bit level compression, so which makes things much more easier from an attacker's point of view. So we are going back to the paper in 2002 by John Kelsey, which is we have a whole compress, then encrypt on all of the data channel. And the effect is much more widely for the whole network traffic that VPN tries to encrypt. So I would like to dub this attack the Oracle attack. So if that's part of homage to my favorite artist called Oracles. I don't know if you guys know him. He's a progressive music guy. So it's a combination of VPN and Oracle. So I was like, everyone has their name, Time, Heist, and Breach. Why not? So there you go. I don't have a logo or a website, so I do some justice there, I hope. The PR team, yeah. So what does it say? The Oracle attack is basically under a VPN, HTTP web apps are still insecure. So if you are using VPN purely to protect yourself from insecure websites, that don't already have HTTPS enabled, for example, you're trying to access a website in your corporate, or if you're trying to access a website who don't know what Let's Encrypt is, or who are lazy enough to not understand that, then those websites are vulnerable. So I want to make it very clear, the impact of this attack. Using a VPN, if the VPN is already trying to encrypt existing encrypted data, then you're all good. So things like SSH or things that already use HTTPS, like google.com or most of the websites today, then you are good. So for the most part of the internet, things are good. And also that adds to a reason, because when you do compression on already encrypted data, it doesn't make sense, because already encrypted data has a lot of entropy. And when you do compression, you're going to eventually end up with more bytes. And from a performance point of view, that doesn't make sense. Your compression algorithm is not doing what it's supposed to do. However, things can go bad for these kind of scenarios. DNS traffic, which is over UDP, and insecure HTTP traffic, pure TCP, and your VPN fully compresses them. So let's see how this stuff works on a HTTP web app using an encrypted VPN. So to talk about this, we need to understand what does an attacker require to conduct this attack. So from a VPN's point of view, you need to have compression enabled for VPN and server and client, obviously, and the attacker can be an MITM. So this could be your ISP, your attacker on the Wi-Fi network, or government, stuff like that. And the VPN user has to visit a attacker controlled website as well. So that's a pretty common use case that you can come up with today, which most of the web app attacks, if you have seen, attacker luring the user into a cross-domain website is more or less easy. So let's look at a setup here. So you have a VPN user who's vulnerable, who's using a specific browser, and who's trying to access a HTTP web app over the internet. Now, he knows that's HTTP web app, so he's going to use a trusted VPN, which is secure. Now, everything goes through the trusted VPN, everything is encrypted, it's all good. And the data channel at the end between the VPN and the compression, the VPN and the HTTP web app is going to be unencrypted, of course. But if you think of corporate VPNs or corporate networks more specifically, these are going to be in a DMZ. So everything, only the VPN is going to be facing the internet, and everything else in the internal region. So that's a very good use case for VPNs in these scenarios as well. So attacker could always, it would be hard for a man-in-the-middle attack on the internet to get into that traffic. So whatever that goes to the internet would be encrypted because of the VPN. Now let's assume an attacker who has capabilities of doing the Oracle attack. Now he can host his own attacker.com, using which he will serve you JavaScript, which conducts the attack. Now, the attacker can do the passive MITM, obviously, and he can also inject ads or any web app and do a cross-domain JavaScript injection. Now, using the passive MITM, he's going to do the first requirement, which is observe the length of the data packet. And using the second one, he can use the browser to send cross-domain requests to the web app, which in fact goes through the VPN, right? So that using this, an attacker could conduct this compression oracle attack on requests and responses. Pretty straightforward. So for the demo here that I'm going to show, first of all, I've been trying to do the demo here. The Wi-Fi network has been creating some problems for me because this does involves brute force with some precision. So I wouldn't be doing an actual live demo. I have a fully recorded video, which I did a while back. So I'll be showing that. Sorry about that. And for the demo, we are going to use Firefox and the VPN client, which you can access here, the OpenVPN/OpenVPN3. That's the latest one. And if today anyone is going to implement their own OpenVPN as a service, they would be usually distributing binaries for Mac, Windows, and mobile phones using this library. So I thought that would be a good target to just do this generic attack. And we are using an OpenVPN server. And for the demo purpose, I've created this website called insecure.skepticfh.com. So that would have its own session, a randomized session. And the goal of the attacker here is to steal the session ID from the cross-domain website, which is attacker.com, right? Okay, so let's take a look at that. You guys see this, hopefully. So what I'm doing here is trying to connect to the OpenVPN server using this OpenVPN3 client. So I'm using my own VPN file, which has compression enabled. That's what most of the SaaS providers give you the OpenVPN file with. So let's start this. So I've connected, and it's using the LZO compression, and for the control channel, it uses those specific parameters. And I've connected to this OpenVPN server. And let's go to Wireshark and look at the traffic, how it looks like. So that's the IP address of my VPN server. And I've just put the frame length more than 300 for looking at data packets. And I open the Firefox browser, and I go and do some stuff with my Insecure web app. It sets a cookie for this website. So in this case, for this Insecure web app, this is the cookie. And as you can see, my client is sending requests to the OpenVPN server, and everything is encrypted. So even everything that goes just right out of the client is going to be encrypted, so the attacker couldn't see anything. Now, I'm doing this MITM, so assume this MITM is running on the internet, right? So this could sniff on all the OpenVPN packets for your target client and the target server that he's connected to. So what this MITM tool does is takes all the OpenVPN packets and forwards it to the attacker server. So we're going to start the attacker server in the other tab here. So it's just a small Node.js server, which listens to this packets from the OpenVPN sniffer and tries to conduct the compression oracle attack. Okay, so let me start the attacker server here. I'm running this locally here, which is on localhost 9090. So the first thing to note here is the other domain is a cross-domain website. It is insecure.skepticfh.com and localhost. And in the real world, this localhost would ideally be an attacker website host on the internet, more preferably closer to the client. So we could make these precision attacks much more easier. And by default, the browser, even though both the websites are in the same browser, the other website cannot steal the session ID cookie. If you could do that you would have a same origin policy bypass. So that's different. Let's go into how this would work. So what I'm trying to do here is try and brute force by sending each requests and try and brute force this cross-domain cookie. So as you can see here, this is my server, which receives packets from the OpenVPN sniffer on the internet. and it just looks at the length. Obviously, it doesn't have to look at the encrypted data. It doesn't make any sense. Just the length, which is the oracle here. And every time it tries to send 10 packets, each with the brute force, each brute forcing the final character of the secret. So if you see when it says guessed 2, which means the, as you can see here, 545, 545, 544. So the first character was 0. The length was 545. The second character was 1, 545. The third character was 2, and you ended up with 544, which means the attacker can deduce this the character 2 resulted in a compression. So that's the compression oracle, and he decides that the guess is 2. So if you eventually do that for everything, you could basically leak the whole secret. Yeah. Good question. Yeah. So by default, so his question was, what about the block size? Aren't encryption algorithms supposed to use 16 bytes of blocks, depending upon the encryption that is being used? Yes. So by default, OpenVPN uses the BF cipher, which is a pure stream cipher. However, if you and the recommendation is to use, obviously, the most advanced AES with GCM and AED and all those things enabled, which OpenVPN does very well, by the way, using its provided OpenSSL wrappers. But even with those, we could do the same attack. This makes my demo and the whole attack easier. But if you have the block size of 16, let's say, all the attacker has to do is add random data, through which he can just offset 1 byte. So by default, he would have 1 extra character while brute forcing, so that it could be on the next block. But if there is a compression, that one extra byte won't be in the next block. It comes back to the previous block. So you would see a reduced length of 16 effectively. So yeah, there you go. And yeah, you have the secret. Thank you. Thank you. Hey. All right, so I'm just randomizing this again just to say, it just works. So now I decode this. As you can see here, it's 5, what is that? Yeah, 5721. So I'm just doing that. It just works. Yeah. Sorry? Yeah, so it depends upon the endpoint that you send the request to. So when you do this actual request, I always prefer sending a request on the server which has static resources like a JavaScript or an image. So this eventually won't hit the actual servers. Even the server might even sometimes cache those requests. So ultimately, there's no the session cookies won't change if you send it to static pages. But yeah, if the cookie changes every time, then this attack wouldn't work. Or if your web app doesn't have an endpoint which has that. Yeah. Yeah, please.
So would the attack really be possible if there were other ways on the channel? Like you've got the applications that are requesting other pages. You're going to get these random link packets that we encrypted.
Yeah. So are you asking how am I able to guess this is the packet that I sent?
Well, yeah, you mentioned earlier that these commercial VPNs might follow this view and like get together people who are all hitting the site with different traffic so you can see the encrypted
Yeah.
side.
Yeah. Exactly. So there is an even bigger problem than that. I'll come about that. No, I'm going to talk about that now, by the way. So let's go to that. Yeah. So, okay, by the way, this whole code and everything will be available, and you can also detect how your OpenVPN is vulnerable or any VPN is vulnerable using this tool. I'll also show you how to do it yourself a little later. But yeah, let's go into the challenges here. So the number one challenge that I found compared to most other compression oracle style attacks is that actually detecting the packet that you sent. So unlike trying to attack a TLS channel, which from the attacker's point of view has the luxury of something known as the SNI, or the server name indication, or even the public certificate of the server. Every time the attacker sends the request and there is a TLS channel which is going to be established, the attacker can clearly see, okay, this is the client from the source IP, and he knows this is the server that is trying to connect. So you could effectively detect the packet that you're sending among a lot of other data which the client is trying to send over the internet. However, in the case of VPN, you don't have this. Every traffic goes to the same server, and VPN is also more chatty. What I mean by that is that every packet, regardless of whether it's a DNS request or if it's a HTTP request or a SSH, it's going to be from the same client to the same server, and all you see is OpenVPN and some bunch of data, right? So there have been some similar. So the way I solve this is by using some form of determining what you send using some form of classification. So if you looked into the history of detecting VPN traffic, so there have been good researches done on VPN traffics on how to detect what site the underlying VPN is trying to connect to. So there have been also good papers on classifiers using some basic machine learning. I tried in my attack, in my POC, as you can see, I didn't use any classifiers or machine learning algorithms, but I used a very simple method which does this more deterministically. So when the sniffer connects to the attacker's server, sorry, I don't have the slides for that, but I wanted to explain this in more detail. When the sniffer connects to the attacker's server, it looks for all these bytes of data. Now, what it tries to do is it tries to classify locally what are these packet lengths, and it sends 10 repeated requests. So if you saw my video, there is a part where I was saying get base length. So the get base length is where I try to determine where can I push my packet size for this attack so that is kind of in an isolated region. So in my attack for this website and this traffic, it was around 550 bytes. So I didn't see any other DNS traffic or any other website traffic which was around that region, because I added junk data which came close to this. So with this, I was able to do this attack effectively. So I hope that answered the question. So we can talk about this more in detail later, because that's I believe is the evolution of this kind of classes of attack where more research work can be done. So also the way your browser sends HTTP requests matters in this context. So the reason I couldn't use Google Chrome here was because when you try to send a post request, which is required for this attack on OpenVPN, Google Chrome, for some reason, split the HTTP request and body into two different data packets. So OpenVPN's compression algorithm couldn't come into effect because the attacker's chosen bytes and the existing secret, which is the cookie, are in two different HTTP packets. Sorry, two different TCP packets, part of the same HTTP data. In Firefox and other browsers, it's just as expected. You send a HTTP packet, the headers and body are in the same request. So your compression window is within the same request. Okay, so detecting Oracle in your VPN. So if you are using OpenVPN, and if your server is using OpenVPN or your provider is using that, you could just look at your client configuration file, which is the OVPN file. And if you have something like compress, LZO, or compress enable, which is the more latest versions for OpenVPN compression, they just use compress enable. So you could detect that and you're probably vulnerable. However, what if you're not using OpenVPN? The better way to determine this for any VPN that you use is dynamically by sending your own request. So it's pretty simple. I have a do-it-yourself checklist for detecting Oracle. All you need is a Wireshark, and you have to be connected to your VPN, and just send some few curl requests and observe the length. So if you understood initially how this attack works, you should be able to do this by now. So all you have to do is copy-paste this curl request, send a request to a HTTP web app, and observe the length. So when you see an unguessed secret which is wrong, you will get ETS. If the secret is 2, ETS still. But if the secret becomes 3 that you're going to guess, the compression should reduce. ETS -1 or ETS -3, whatever it is. and you should see a reduced length in your Wireshark for that specific packet. So if that is possible when you're connected to your VPN, your VPN is probably vulnerable for HTTP traffic. Okay, so FITSing. In general, FITSing compression is a very opinionated area. It's very interesting from the performance point of view, from the security point of view. How effective is this to even disable entirely? So when the crime attack came about, if you remember, they talked about the speedy protocol and how the headers in those were a problem. So for later HTTP2, they came up with this protocol called HPAC. It's pretty straightforward. What it tries to do is selectively disables compressing sensitive data. So in this whole attack that we've been talking about for crime and even this attack, if you could selectively disable cookies from getting getting compressed, then things would be safe. So if you look at the HPAC specification for header compression, they have this thing called never-indexed literals. So there they maintain a list of well-known literals which are sensitive. So if you're using an algorithm to compress stuff, you probably want to know this never-indexed literals and probably add them to your library as well. And Cloudflare, they're interesting. They're doing some interesting stuff here as well. So breach attack that we talked a little while back is not entirely fixed because you can't simply go and fix gzip or just disable HTTP response with the enormous amount of web apps that you have today. That's going to be crazy. So they did a similar thing, just like the never-indexed literals. It's kind of like a challenge. They have their own breach-style website, which is vulnerable to breach, and they have this Nginx module called CF no compress, which selectively disables compression for the well-known secrets that they use. So in this case, that's CSRF tokens and other stuff in the HTTP responses. So my specific advice for VPN authors and library implementers in general is to disable compression entirely if you have HTTP traffic. Because if you have users who are using your library purely for encrypting HTTP, then they're going to be misled. So as I said, entirely turning it off is opinionated. When I had this discussion with the OpenVPN team, they're a nice bunch of folks. So they couldn't entirely disable compression, even though they had two camps which said want to go ahead and completely disable. But a lot of people are using OpenVPN, and they chose to effectively warn every users of OpenVPN. So one instance is TunnelBear. It's one of my favorite SaaS VPNs. And I had a chat with them. They quickly disabled compression on their server side and on the client side. So that was pretty neat. So as everyone have been saying, it's time we move to HTTPS. It's nothing new. People have been saying this for 15 years. We have Let's Encrypt. We have a lot of HTTPS is really fast now. Like if you use HTTP2, it's a lot of crazy things happening there with TLS 1.3. Things are much, much more better now. So I don't see there is a reason for anyone to still use HTTP, or even someone's using HTTP or VPN. Now is the time to just move away from that. So as I said, the takeaway, if you are a end user, talk to your web app owner or your corporate web app guys to just move to HTTPS for those specific traffic that they send. And if you are still using VPN to protect against plain HTTP traffic, don't do that anymore. And VPN providers, as I said, try to disable compression or do the never-indexed literals like CF no compress or HPAC. So that's it. Thanks a lot.